Hey everyone, we're looking at CR7.2 acids and bases. Here are the education perfect slides, activities that you should be doing after watching this. Looking at pH and dilution, neutralization reactions, and then you can look at acid reactions with metal oxides and hydroxides, and metal carbonates and hydrogen carbonates. Just quickly, the acronym that I've been using for reminding you about neutralization reactions is BAWS. This can be found on your information sheet on page 4, where a base with an acid will produce water and a type of salt. Salt being not typically, a metal ion and combined with a non-metal ion or polyatomic ion in some cases. pH is the way that we measure how acidic a substance is, or how strong the acidic substance is. And these reactions here, the acid reactions with metal oxides, as in something, a metal and oxygen ions, or hydroxides, which we know as OH -1. Metal carbonates, so carbonates being the polyatomic ion CO3 with a -2 charge, or hydrogen carbonates, which have a HCO3, which has a -1 charge. That is because the hydrogen ion, it has a +1 charge. So overall, a hydrogen carbonate ion has an overall charge of -1, because carbonate is -2 and hydrogen ion is +1. So going back to CR7.1, where we were talking about strength versus concentration of an acid. Strength is talking about how well an acid dissociates its protons or its hydrogen ions, and a strong acid has the ability to fully dissociate. The word opposite to associate. So a strong acid, just like hydrochloric acid, will fully dissociate, whereas acids that come from carboxylic acids, chemicals that have this Q or this COOH structure, these protons, these hydrogen ions, will partially dissociate, typically at a 1:100 ratio. For every 100 molecules of acids that are carboxylic acids that have this Q group, one of them will dissociate their proton. Concentration, talking about the, you could talk about the concentration of molecules of acid, or you could be talking about the concentration of hydrogen ions. And the concentration of hydrogen ions is how we measure pH. So we're going to get into that. Okay. So let's take a look at what the slide provides. So this is a scale based on powers of 10, measuring acidity or alkalinity, which is another word we use for basicity or how basic a substance is. pH is specifically measuring acidity. Whereas basicity is typically measuring the concentration of hydroxide ions. So that's written as POH instead. But we'll ignore that for now. So pH, looking at acidity, is based on powers of 10, just like the Richter scale for earthquakes. So what we mean by that is if we have an earthquake of a Richter scale of 5, earthquake, it will be 10 times more powerful than a Richter scale 4 earthquake. So that is 10 times more powerful. And a Richter scale 3 earthquake would be 10 times less powerful than an earthquake of Richter scale 4. And what we need to be careful about is when we're comparing, say, an earthquake of a magnitude of 5 compared to a magnitude of 3, it's not 20 times more powerful. It's actually 10 times 10. So that would be an earthquake that is 100 times more powerful than Richter scale 3. So likewise, but in the reverse order, we have, if we were looking at pH, say 3 versus an acid of pH 4, an acid of pH 3 is 10 times stronger than an acid at pH 4. And it's in the reverse order when looking at earthquakes because the way that we measure strength of acidity is going down in terms of numbers. So on the pH scale, where we have 7 for neutral substances, at pH 0, as we go towards 0, substances are considered to be more acidic as you go towards 0. So the smaller the number, the more acidic the substance is. And there you go. So it's an inverse relationship. Inverse meaning the bigger this number is, the bigger the concentration of hydrogen ions is, the lower the number we use for pH. So a pH 2 acid is stronger than a pH 4 acid. And because it's a powers of 10 scale, then pH 2 acids are 100 times stronger than pH 4 acids. Now, this says the greater the OH hydroxide ion concentration, the higher the pH, and that might be confusing. That's because the greater the concentration of hydroxide ions, the lower the concentration of hydrogen ions. And back on the pH scale, where we have neutral substance at 0, acidic substances neutral substance at 7, and more acidic substances towards 0. In the other direction, towards the number 14, we have substances that are of increasing strength of bases, or we could say that they are weaker in terms of acidity. Okay. So pH is on a logarithmic scale, and we're going to be using a formula that requires the use of logs, base 10, which your calculator is set to default on when you use the log button. So this says that the lower the pH, the greater the solution's acidity, and giving the example like what I've explained to you before, where a pH of 3 is 10 times more acidic than an acid which has a pH of 4. pH 7 is considered to be neutral at 25 degrees, and the higher the pH, the greater the solution's alkalinity, the word which is used interchangeably with basicity, or a basic substance, or how basic a substance is. So if we're describing it in terms of alkalinity, then the numbers work in the opposite direction. So be careful in terms of what it is that the question is describing, if it's describing acidity or it's describing alkalinity. So larger the number, the more alkaline solution is, and in fact in powers of 10. And if you're talking about acidity, then it's increasing by 10 times as you go towards 0, or you go lower. Okay. Now, in year 10, you would have looked at, and even year 9, you would have looked at the pH scale between 0 and 14. But the scale does extend beyond the numbers of 0 to 14, and we can have extremely acidic solutions with a pH of -1 and pH of around 15 for extremely basic solutions. And again, with your pH scale, making sure that you understand the basics, where pH scale goes from with the 7 in the center for neutral substances, and as you go towards 0, substances are becoming more acidic, and as you go towards 14, substances are more basic. All right. So the pH scale is used to indicate how acidic or basic something is by looking at the concentration of hydrogen ions. Yeah, that's all fine. You can just read that. Yeah, so if they're closer to the number 7 in terms of pH, say 6 or 8, we would say that they are weak, because the further away you are from 7, the stronger in terms of acidity or alkalinity the substance will be. Okay, so 7 is neutral. Yeah. So a chemical that changes color as pH changes is called an indicator. You've had experience with this when you were looking at the red cabbage indicator practical in year 9. You would have extracted a chemical which makes red cabbage that color, and which is called anthocyanin. So that's the name of the indicator found in red cabbage. Uh, it changed. It changed many different colors depending on the pH of the solution that the red cabbage indicator was in. So you'd have used it to identify unknown substances of varying pHs, because you would have known what color matched with what pH from your testing. So that's all what an indicator does. It indicates the pH of of a solution, and all you need to do is add it. Now, the way an indicator works isn't for you to understand, but basically what it does is it changes the way that light moves through the chemical, the indicator substance, and it will vary based on the chemical's interaction with the protons, the H pluses, from the solution. But you don't need to know that. There are many indicators, and you can see here we've got universal indicator, which has a different color for each whole number across the pH scale from 0 to 14. Phenolphthalein, this phenolphthalein, if you will, has a range of color. No, it only has one color change. And then, as you can see here, phenolphthalein remains colorless between pHs 0 to 8, roughly, and will turn pinkish beyond that. And so there are some indicators that will have one color change and others that have two different colors, and where they change in terms of pH, it just depends on the type of indicator that you're using. And so we would select indicators based on the pH change that we're interested in when we're doing a chemical reaction, which will become important when we do titrations. All right, so here are some questions for you to think about. Some that are just testing, do you know that acidic substances are more acidic when looking at their pH? And so if you've got a substance that has a pH of 3.4 and 4.3 for the other solution, then the smaller value, the one closer to 0 is the one that is more acidic. Here we have a question that is more challenging. We're asking which one would have the lower pH. We have 2.15 moles per liter solution of sulfuric acid versus 1.5 moles per liter solution of sulfuric acid. So quickly, you can determine that the higher concentration of sulfuric acid will be the one with a lower pH because pH is a measure of concentration of H pluses, of hydrogen ions, the thing that makes a substance acidic. So if you have more hydrogen ions in higher concentration, then that substance will automatically be more acidic, and substances that are more acidic will have a lower pH. Yeah. So even though it's the same substance, they're both sulfuric acid because the concentrations are different, and this one is higher, then that is the one that has a lower pH. Lower because the lower the pH, the more acidic the substance is. And big M, confusingly, big M so far has meant two different things. We've used it to say that it is looking at the molar mass of a substance, and now we're talking about it meaning molarity, which is another word we use to describe the concentration in moles per liter, or mol to the negative 1. Okay. Question 16 here. Which would have the lower pH? We've got a 2 moles per liter solution of a strong acid, sulfuric acid. Strong meaning what? Strong meaning that it fully dissociates or fully gives away or donates all of its protons, all of its hydrogen ions, compared to a 2 mole per liter solution of a weak acid like carbonic acid. Okay, so things to notice here. The first thing we need to understand is that the question is highlighting the fact that both of these solutions of acid have the same concentration of the molecule of the sulfuric acid and of the carbonic acid. So they have equal concentration of those substances. But what determines acidity or pH is not the molecule itself, but rather the number of hydrogen ions that they can donate. And because sulfuric acid, being a strong acid, would donate all of its protons in comparison to carbonic acid, which is a known weak acid, that automatically tells us that the sulfuric acid is the one that would have a lower pH. Because weak acids partially dissociate their protons. And the last question here, I think, which would which would have the higher pH? Okay, so we want to make sure that when we're reading questions, we're reading them carefully. So higher pH meaning either a weaker acid or a substance with a lower concentration of hydrogen ions, or on the flip side, if we're talking about bases, then we would be talking about numbers that, sorry, uh, if we're talking about bases, then the higher the number for the pH, the stronger the base will be, or the weaker that acidic substance would be. So if we're talking about bases, then we want to know, and we want to know which one is higher, then we want to look for the stronger base. Stronger bases will dissociate all of their hydroxide ions, and weaker bases will partially dissociate their hydroxide ions. So if the concentration is the same, then the weaker base will have a lower pH than the stronger base. I don't know why this word acid is there. That's wrong. That needs to be gone. Okay. On a side note, you can calculate the pH of a substance by looking at the concentration of hydrogen ions and using a formula, but that is something that we don't need to do. So I won't introduce that formula so that you don't get confused. So if you're asking, well, how would I calculate it? I don't think a question will require you to do that, but rather just doing a comparison in terms of strength of acid and concentration, and potentially asking you to compare things like monoprotic acids and diprotic acids. So keeping, not starting this dilution slide yet, but if you had if you had 1 mole per liter concentration of HCl versus the same concentration of a diprotic acid, both of them strong, then which one would be the stronger acid? So both they're both strong, which means they both fully dissociate their protons. They're both the same concentration in terms of molecules of sulfuric acid. I keep doing that. Sulfuric acid and hydrochloric acid. However, the difference is that hydrochloric acid is monoprotic and sulfuric acid is diprotic. And so sulfuric acid would have double the amount of hydrogen ions to donate. Therefore, the stronger acid, sorry, not the stronger acid, the solution, if we're comparing, say this is 1 and 2, comparing those two, we would say that the sulfuric acid would have a lower pH because it would have more protons per liter because it's diprotic. All right. Setting that aside, we've got here dilutions of acids and bases. Okay, so we've looked at this formula. Whoops. This one is given to you on page 5 of your information sheet, and it's measured in terms of moles per liter. So volumes measured in liters and moles there. So therefore, if that's moles and that's liters, then concentration, because it's moles divided by liters, concentration, its unit of measurement is moles per liter, or written like this. You can see here it's also known as molarity. Which we use capital M for. The most convenient way of preparing a solution of a dilute acid is by mixing a concentrated acid with water. So we're making it more dilute by adding more water. So even it will have the same number of moles in the entire solution, but it will be more dilute, because dilution or concentration is talking about moles per liter. All right. So what they've done here in this diagram, going from left to right, we've got 10 mils of 10 moles per liter concentration of hydrochloric acid using a pipette, which is this device here, with a bulb on top to change pressure to suck liquid up. We're only taking 10 mils, and then we're transferring it to a volumetric flask, which with the size of 100 mil. So if you can see, volumetric flasks are designed to do one thing, and that is to measure exactly a single volume, just like a pipette would. So that line there would be exactly 10 mils, and this line here on a 100 mil volumetric flask would measure exactly 100 mils. So we're adding the 10 mils of 10.0 mole per liter HCl using the pipette, and then we're transferring it into this volumetric flask, and then we're filling the flask with distilled water, so water that has less random bits of stuff in it, to the calibration mark, which is this line here, which would be exactly 100 mil. So in this case, we will be adding exactly 90 mils of water to the 10 mil of 10.0 moles per liter of HCl, and then for a total volume of 100 mil. That is a dilution. So whatever number of moles that was in the 10 mil would now be spread across all of this. So if we want to calculate exactly how many moles is in here, when we pipette it out, we would go, all right, I know that the volume I used was 10 mil, So that's the volume. And we need it to be in liters. So we would divide it by 1,000 or times it by 10 to the negative 3. And we know the concentration, which is 10.0 moles per liter. Therefore, we can find out number of moles because we know there's a connection between those three variables. So because I know this, and whoops, lol, because I know concentration and volume, if I multiply both sides by volume, I would get the formula to rearrange to become this. And then I can find out how many moles of HCl is in that 10 mil. So 10 mil times 10 to the negative 3, or 10 divided by 1,000, would be 0.01 liters. So I would go, well, the number of moles of HCl in this situation here is equal to 10 times 0.01, and that's equal to 0.1 moles of HCl. So if I have 0.1 moles of HCl, then in the volumetric flask in this, even though I'm adding more water, I would still have 0.1 moles of HCl, but I have it in more volume, which means the concentration has now been diluted, and I can calculate that. Okay, so because the total volume is now 100 mil, so 10 mil of the 10 mole per liter acid and the 90 mils of water that I added, I can calculate the new concentration. So because concentration is equal to number of moles over volume, and I want to calculate the concentration, I don't know that. I do know the number of moles from my previous calculation. I know the new volume, which is 100 mil, converted to liters, 0.1 liters. Then I would go, okay, concentration of the new HCl is equal to 0.1 divided by 0.1. Same number divided by same number is equal to 1. And 1 what? Well, concentration is moles per liter of HCl. So that's a dilution of making 1 mole per liter concentration of HCl from a 10 mole per liter concentration of HCl. So like I've been saying, when you do a dilution, the quantity, not the concentration, but the quantity of the solute does not change, okay, as indicated from the previous slide. What changes is the volume of the solution when you do a dilution, and therefore concentration has to decrease because there's less moles per liter now. So we can calculate that, we can shortcut that by using this new super formula. So that comes from N equals C over V. I will try and explain it again, but if you don't understand why this formula works, what you need to know is how to use it correctly. So what we want to highlight here in the formula is this subscript here, the subscripts 1 and 2. So we want to use, because we're looking at the concentration volume of before and after, of the before and after of dilution, it's important that you use the numbers correctly. So I would normally save the ones for information relating to the initial solution, or the more concentrated one, and I would use the 2's for information relating to the final solution. In other words, the dilution. So all those calculations I did on the previous slide, you could do in one step. So you could have done, we knew the concentration for the initial solution, was 10.0, and the volume that we used to make the dilution was 10 mil, or so 10 times 10 to the negative 3 liters, or you could just say 0.01 liters. And we didn't know the concentration. That's what all we want to know when we do a dilution, but we knew the final volume. Now, final volume, you can get tripped up by this because in our previous slide, we knew that there was 10 mils of that HCl, and we had to make it up to 100 mils using 90 mils of water. Be careful to not use the 10 or the 90. The final solution's volume will be the total every time. So the volume we're going to use here, and making sure it's in liters, V2 was 100 mil, which we would convert by either doing this on our calculator or dividing the 100 by 1,000, which is the same thing. So our final volume in liters is 0.1. Okay. So if C1 V1 equals to C2 V2, then what we can do is rearrange the formula so that C2 is by itself, which means we're dividing both sides by V2. So we end up with a rearranged formula that's gone from C1 V1 equals C2 V2, and we've rearranged it to become C1 V1 divided by V2 equals to C2. In other words, using all of this data here, whoops, did it again. That, and that, we would plug into our rearranged formula, and so we would go, well, C1 is 10 times the volume, which was 0.01, divide that by the final volume of 0.1, and that is going to give us 1. And that's the final concentration. So that's all all the steps from the previous slide in one calculation. Okay. We can also make dilute bases as well. So the reason why we do this is because when we buy acid from a company, we will get acids of HCl at like 36 moles per liter. Really, really concentrated stuff. So in order to be lab safe, color camera, in order for it to be lab safe, we need to dilute it to a concentration that's safe to work with. There's still some hazards related to it, but safer than 36 moles per liter. And we can do the same for bases. We can do some for bases. Solutions of base of a required concentration are repaired by diluting, or you could also just do this. You can just dissolve a weighed amount of a base in a specific volume of water. So you would have to do a mole or a mole calculation so that you would know exactly how much of the base you would use, and then you would put that into a known volume of water. So if you wanted to make, I don't know, 2.0 uh, 2.0 moles per liter NaOH, for example, and you wanted to make 2 liters of it, you would figure out, well, in 2 liters of this concentration, I would need 4 moles of NaOH, and then you would just do N equals M over capital M, rearrange it to become mass is equal to number of moles times molar mass, and then you would go 4 times the molar mass of sodium hydroxide, which would be 22.99 plus the 16 plus the 1.01, and then, wait, 01? No, we use 0.8. And then you would find out the mass of the sodium hydroxide you would need to make this concentration. Oh, I did it again. Sorry, my bad. Oh, there's a diagram. There you go. Accurately measure out a mass and then transfer it to a volumetric flask. Make sure you're using it's completely clean. Dissolve the base in the water. Add water to make sure it's the correct volume so that you will have what you need. Okay. Give an example of a solution that is a concentrated solution of a weak acid. Oh yeah. Give us an example of a solution that is a dilute solution. So a number smaller than 10, maybe a number of maybe 1, maybe 0.1. 0.1. Pure sulfuric acid is approximately 16 moles per liter. In order to prepare a dilute solution, the concentrated acid must be dissolved. And so we've got a question here that says, what volume of 17 moles per liter of sulfuric acid will be required to make 10 liters of a dilute solution of sulfuric acid with this concentration? Okay, so we know to use the C1V1 equals C2V2 formula because it's a dilution question. It's a concentration becoming a different concentration question. And because this formula has concentration twice, that's cluing you in to use this. And this is a formula you need to remember because it's not provided. Okay, it's a combined formula. So all you need to do is identify correctly the bits and pieces that you have and then figure out the formula, then rearrange it for your use. So using 1 as being initial or the concentrated, and using the 2 as the final or the dilution, then we can say, well, this concentration here is referring to the concentrated form of the acid. So we're going to label that C1. That's the concentration for the initial. We've got a final volume we want to make of the dilute acid. So that final being V2. And we want that final concentration to be 0.5. So then we call that C2. So I've got in my calculations, my preparing for calculations, I've got this C1, I've got concentration for the final dilution, I've got volume of the final dilution, and the question wants me to confirm what volume do I need. So that's confirming that that's the one I don't know, therefore that's the one I need to calculate. Therefore, to rearrange this formula, I need, because this is the one that I'm trying to figure out, volume, I'm going to divide both sides by C1 to remove that from the left-hand side to make the formula volume of what I needed is equal to C2 times V2 divided by C1. And then I'm just going to plug those numbers in. The volume that I need is equal to 0.5 times 10 divided by 17. And my calculator says that that is it says that it's equal to 0.294 liters. Units is important, and you'll notice there I used 3 significant figures, and that's because the question is using 3 significant figures in all of its values, and it's the least and most, but the more important part is the least number of significant figures being used in that question, so therefore that's the one I'm sticking with for my answer. Reactions of acids. Okay, these 3 are given word for word on your information sheet on page 5, so you don't need to remember these, but you might need to know what's going on here with the carbonate, because technically speaking, a carbonate is just what is happening? A carbonate is just a CO3 negative 2. And so what we mean by reacts with the carbonate is it's reacting with either a metal carbonate or a metal hydrogen carbonate. I'll give you some examples. So a metal carbonate example would be like sodium carbonate. So sodium, 2 of those, because each sodium is +1, and because carbonate is -3. Or sodium hydrogen carbonate would be one of those, and that. Magnesium carbonate, because it's +2, would be MgCO3, because that's +2 and that's -2. Calcium carbonate, CaCO3, etc., etc. So the salts that are forming would be the metal part of either the base, the actual metal itself, or the bit that's not the carbonate. So in this case, the calcium, the magnesium, or the sodium. So the middle part of either the base or the carbonate, and the other bit will be the bit that comes from the acid that is not H pluses. So give you an example for that. Let's do one for each. Okay, so let's do Sorry, the camera's out of focus, so I'm holding the tablet at the same time. I know you want to see my face. Sure. Anyway, an acid like HCl, a common base, sodium hydroxide. How do I know it's a base? Good clue is that it's got a hydroxide ion. Okay, so we know it forms water. So there it is. The salt comes from the metal bit, okay, and the bit that's not the protons from the acid. There we go. Uh, I'm not balancing these equations, so don't worry about that. Acid, metal, salt, and hydrogen gas. Okay, so let's use a different acid. Let's use H2SO4. What metal? Let's use magnesium. So hydrogen gas is just H2 in its molecular form. It's in everyday form. It's always H2. So the salt would be the metal, okay? And the other bit of the salt will be the part that's not the protons from the acid, okay? And I'll give you another example. Let's go HNO3, nitric acid, and the carbonate we'll work with will be calcium carbonate. Okay, so we know it makes water and it makes CO2. What's the salt? So the carbonate is going to be responsible for um, the the oxygen on the water and the CO, well, all the bits of the carbon dioxide. That's those. I'll highlight that in green. Uh, those parts will be from the carbonate ion. Okay. And the salt will be the metal bit from the metal carbonate or metal hydrogen carbonate. And the non-metal part of the salt will be the bit that's not the proton of the acid. And because NO3, because nitrates are -1 and calcium is +2, we need 2 of these for a correct formula. There you go, there's an example for each. Um, Emphasizing what is a salt. All right, this is not accessible, but just for your curiosity, if you're like, why does it do that? We already know uh, we already know that acids are proton donors, and they will do that when dissociated in water. Because they're positively charged, they are attracted to negative stuff. So the electrons, or you could say the negative ions, because they have a lot of electrons. And then you can have H pluses to form gases or to form other stuff, but don't worry about it this slide. All right, recognition. Okay, so I've gone through a bit of this, but I'll go through it again. Um, I mean, although it's already given to you in the information sheet, BAWS, BAWS is the acronym I like to use. And you can see that they do swapsies, which we've looked at. The proton from the acid and the hydroxide from the base will produce the water molecule, and the remaining bits, the chloride ion and the sodium ion, will make the salt. With this one, which I like to call MASH, okay, will then produce hydrogen gas, so H2. That's all from the protons donated by the acid. And the metal will become an ion. So this Na here is Na plus 1. And then the non-metal part of, sorry, not non-metal, the part that's not the proton of the acid will then become the salt. Metal carbonates. This one, I have it's a weird acronym. I just say McCaw CD, and I just imagine like a parrot. A parrot releasing an album, McCaw CD, and that's for metal carbonate, so that's MC. Acid makes water, salt, and carbon dioxide. But it's there on your formula sheet, so that's not a problem. Um, you don't need this acronym, but it's about recognition and being able to see these three reactions quickly when you're doing a question. And so we have an acid and a metal carbonate here, CO3, with our sodium ions. And you can see it makes water and carbon dioxide from the carbonate. And then one of the oxygen goes to the water. And then the bits left over, the non-proton part of the acid and the metal part of the metal carbonate will form the salt, as you can see. Here's a definition for salt. It's an ionic compound, but we haven't done types of substances and bonding yet. So um, just for your information, at this point in time, an ionic compound is a compound made of ions, okay, which is different to stuff like this, water, uh, and just like metals, like magnesium. So how do you know if it's an ionic compound? Well, a good clue is that it's made of a metal and a non-metal. And this non-metal can be monoatomic, as in one atom, or polyatomic. So for example, we've got mono as in one type of atom, uh, mono, poly, mono. But these are all metals: potassium, aluminium, iron, gold, tungsten, I don't know, mercury, and lithium. And as you can see here, Dr. James has said, like, NaCl is not the only salt, but it is the salt that we all eat, but it is a salt. One type of salt, not the only salt. Salts, because they are ionic compounds, water is really good at causing them to dissociate. So this is what this page is about, this slide. Salts, when dissolved in water, will break apart to form their positive and negative ions. This is a strange and different way to basically say positive and negative ions. Okay, so you can see all the examples there. I don't have to read them out for you. I'll just do one with you. For example, when we react hydrochloric acid and potassium hydroxide, the potassium and the chlorine are going to form potassium chloride, but in solution, in water, when dissolved in water, they will exist as separate ions. It's not until you evaporate all of the water that they will combine back together to make potassium chloride or KCl. Practice questions. Write balanced chemical equations for the reaction between, yep, and answers, and some random video about reactions, which we can watch later at some point. All right, that's it from me. Sorry that I'm away. I have to take care of my family. Whole family's sick. Wish I was there with you guys. I'm gonna upload this now. Peace out.